Hello and welcome to the second video on differentiation. Today we're going to go into differentiation proper. And before that, I want to introduce you to a new word, calculus. What does it mean? And maybe give you a brief overview on what differentiation is all about. So let's jump straight into the action. So over here we have the notes. You see a word, calculus, introduction to differentiation. What does calculus mean? Right, so calculus comes from the word calc, which means small pebble or small stone. And you'll be thinking like, what has this got to do with mathematics? And yeah, before we invented numbers, that's how people keep track of things. Like for example, if you were a farmer and you send your sheep out to eat grass, to graze, right? And in the evening, you wanted to make sure you didn't lose any sheep. And what you do is use small pebbles to keep track of how many sheep you have. So when they went out, you count by putting maybe pebbles on the table. And when they come back, you count back. You move one small pebble for each sheep that came back. And then you make sure you didn't lose any sheep that way, right? So that's how numbers were invented from small pebbles. But of course, the word calculus has nothing to do with pebbles. You're right. Calculus is about change, right? In fact, it's about change at a very small scale. Yes, small continuous change, yeah, which is why we use the word for small pebble, right? And under calculus, right, we have calculus is a very, very big umbrella. And under it, we have two main topics. Number one, which you see over here, that is differentiation. Okay, and number two is integration. Okay, so these two are very, very big topics. And differentiation is really about finding the gradient, because the gradient gives us a lot of insight into information, right? A lot of information and insight. For example, if I have a distance versus time graph or distance time function, the gradient will tell me how the distance is changing with respect to time, which means I'll be able to find the speed. Yeah. So if I have a speed versus time graph or speed time function, then the gradient will allow me to find out the acceleration. Okay, so yeah, gradient gives you more information than what you see on the surface level, right? It gives you insight. And integration is about area under the curve, under the graph, which I will not talk about because you're going to see it in a few months' time, right? Integration. So that was fast, but I think I've answered the first question on our checklist. What is calculus? Calculus is the mathematics of change, right? And under this mathematics of change, we have two topics. One is differentiation, which talks about gradient, and then a few more months down the road, you'll see integration, which talks about area. Okay, yeah. Next, I'm going to answer a question that I left behind from the first video. Who are these two guys? Yeah. So if you, towards the end, I kind of revealed that these two guys are, the people who are majorly given the credit for discovering calculus. Okay. So let's start with the guy on the left. This guy. Okay. From the description, you probably can guess who he is, right? Famous English physicist. Apple drops on the head. That is Sir Isaac. And the units for forces, newtons, right? Sir Isaac Newton. Yes, so other than discovering gravity and being a physicist, he was also credited with the discovering of calculus, something in mathematics. Okay, now on to the guy on the right over here. He is lesser known, not as well known as Newton, but he also made a very significant contribution to calculus. His name is Gottfried Wilhelm. Yes, there's a V, because in Germany, W is pronounced as V. Leibniz. Okay, he's a German polymath. Okay, polymath means a man of many talents. Not too sure what Leibniz was good with, right? But an example of a polymath would be someone who is good with math, sciences, art, music. Yeah, just an all-round multifaceted talent. That's what a polymath means. Okay, so why do we have to know about these two guys? Well, for fun, I think knowing the background makes calculus a bit more interesting, differentiation a bit more interesting. Okay, so here's a little gossip on this too, or something interesting first, right? Something interesting. You would think that these two, one guy is based in the UK, the other guy is based in Germany. They're both in the continent of Europe. You would think that the two of them got together and discussed on the idea of calculus and thereby discovering it together. Turns out that is not the case, right? What happened was these two people, right, they were on their own separately. They sort of discovered it on their own, sort of, because they had help from other people, of course. And they discovered it around the same time, right? One guy in the UK, one guy in Germany, right? They discovered the same idea around the same time, okay? So here's some gossip. The two of them didn't get along, right? Because they were busy debating about who was the first to discover calculus. But it doesn't matter because today we credit the both of them for discovering calculus. Yeah? So I think that's really interesting. So who are these two guys? Newton and Leibniz. Okay. So we're going to go into differentiation. But before that, since differentiation is all about gradient, I'm going to do a quick review on gradient. Okay. If you find any of these unfamiliar, I would strongly suggest that you go and revise on gradient. Okay. Gradient, as I would like to put it, is just rise over run. Yeah. Because it reminds us that very fundamentally, if I have a slope that goes like this, right? If I'm going upwards, slope, and I want to know how steep this slope is, right? Then all I need to do is measure, right? What is the increase in height by the time I get to the top of the slope? And then I divide it by how much horizontal distance I traveled along here. This is the run, this is the rise. Yes? So if you had a, say, a steeper slope, it would look like this, and you realize that the rise is higher, and the run is perhaps also, shorter, thereby giving you a greater gradient. So gradient is rise over run. Okay, some of you might be more familiar with the formula. Say if this slope exists on the Cartesian axis, so you have two coordinates, right? I'm going to call this one at the end x2, y2. This is x1, y1. Okay, and you know that maybe you memorize the formula is y2 minus y1 divided by x2 minus x1. Yes? Okay, what is y2 minus y1? That is the rise, isn't it? Because when you take y2 and you minus y1, you're finding the change in height. And if you take x2 minus x1, right, you're finding the change in the horizontal distance. So this is essentially just rise over run. Okay? Yeah, so that was a very, very quick one. So, on to, okay, let me check that off on the checklist. That's number 3, gone. Ta-da. Okay, moving on to number 4. Some of you might have clicked on this video because of the thumbnail, right? How do you find the speed of a car from a photograph? Okay, so let's look at this nice photo of a car. Here we have a Ferrari Formula 1 car, right? This was taken, I think, in 2020. My guess is 2020, or is it 2019? I'm not too sure. In Hungary, right? So if you're a racing fan, do let me know. Was it 2020 or 2019? Not too sure. Okay. But here is the important question. Can you tell me how fast is this car? Just by looking at the photograph. Right? The answer is you can't. You can't tell what's the speed of the car from a photograph. Yeah. But the more important question to ask here is why? Why can't you tell the speed of a car from a photograph? Right? I know some of you are like, hey, come on lah. You need a car to be moving, then you know what speed, right? Yeah, but let's think about this mathematically. What is it that you're missing? What is stopping you from, working out the speed of the car? So keep this in the back of your head. We're going to answer this really, really soon. For now, let's go back to the notes, right? So let's look at this. Okay. So let's imagine ourselves in the shoes of Sir Isaac Newton. Let's sit ourselves down below an apple tree. But instead of having the apple fall on our head, let's have it fall to the ground. Okay. So I'm going to say maybe if the apple is 2 meters above the ground and it takes 1 second to hit the ground. Yeah. Then I'm going to give you the same kind of constraint as our racing car. I'm going to take a picture, right, of the apple at this point in time, right? Because I want to know what is the speed of apple at this point in time, noted by this green point over here. Yes. If I show you a photograph of the apple, would you be able to work out speed of the apple for me? And you say no. But this time you'll be a bit more clear on why you can't give me the speed. That's because in order to work out speed, you need to have 2 points. It's like working out the gradient on the distance time graph, isn't it? Right? You need a y2 minus y1 over x2 minus x1. So what technically you need is another point. Yes, you need another point, say over here. Then you can find the distance, the difference in the height and the difference in the distance, the time. Then you can work out the speed. Yes? Okay. So that was the answer to the question. How do you find the speed of a car from a photograph? The fourth checkpoint. You can't. Right? You need at least 2 points in time to compare to find the speed of a car. Okay. Now coming back to this question, we don't need 2 points because actually there are 2 points already. If you remember, the apple starts from the tree. So right over here, sorry, let me use blue. Right. At 0 seconds is 0 meters from tree. And then at the very, very end, after 1 second is 2 meters from the tree. So we can work out the speed of the apple, right? So that is y2 minus y1 over x2 minus x1. Okay, or as I like to think about it, rise over run. This is the rise. Okay, this is how much change in this in height of the apple, which is 2 meters, right? Over how long did it drop? 1 second. So this is the same as 2 divided by 1. And then you get the time. You get the speed, 2 meters per second. Yes. So that means to say that, hey, the apple is 2 meters per second here, is 2 meters per second here, 2 meters. Something just doesn't make sense, right? How can the speed of apple be 2 meters per second throughout its entire journey? Right? I don't think that is possible. Okay, here's a look. Okay, I'm going to show you a YouTube video. Here's a look at how things actually fall. Here you go. Let's look at this. Okay, so here we have a teacher dropping a ping pong ball 1 meter off the table. And I want you to pay particular attention to the speed of the ball as it is dropping, right? I want you to notice if there's any difference between the speed of the ball when it's released and when it is dropping after a while. Okay, it's going to drop it at 36.2. Right, yeah. So in case you didn't catch that, let's watch that again. At 36.2, he's going to release the ball. Look at how fast it is dropping. Okay, you can use the ruler, kind of measure it against the ruler to see how fast it's going. Yeah, so hopefully you caught that. Yeah. What you notice is that the speed of the ball as it is released is kind of slow, but it becomes faster and faster as it becomes closer and closer to the table. Yes. So I'll say that, you know what, actually this straight line graph is not a good model, not a good representation of the actual situation. Because if you were to drop an apple from a tree, it'll probably be the same as the ping pong ball, isn't it? Right? I will say that, speed of the ball would probably be, or rather the distance traveled by the ball as time passes would be something like this. Isn't it? So why this curve? Okay. And we can just look at this way. Let's split 1 second up into 4 different periods like this. Right. In the first period over here, in the first quarter, this is the distance traveled by the apple. Right? Not much. That's because the speed is not that fast in the first quarter of the second. Right? And then if you look at the second quarter over here, this is the distance traveled in the second quarter. Yeah, a bit more than the first one because the apple is becoming faster and faster now. And then you see the same trend going on in the third quarter, even more distance travel, and in the last quarter, a very significant increase in the distance travel because the apple is becoming faster now. Yes? Okay, so I think this curve is a better representation of the trajectory of the apple as it is falling from the tree. Okay, so now, say, yeah, we have this orange curve, right? The one that I drew just now. Okay, let's go back to our question again. If I give you a snapshot photograph of the apple at this point, okay, can you find for me the speed of the apple? Right? Can you find for me the speed of the apple? Okay, so I know some of you will be like, oh, to find the speed is to find the gradient to find the gradient means that we can draw a tangent line. Yeah, we learned that before, right? Drawing a tangent line. The tangent line will have the same gradient as this point on the graph. Okay, so a tangent line looks like this. Okay, it's basically a line that brushes across the orange graph and only touches the orange graph at a single point, at one single point. Okay, let me make this a bit thinner so that we can, yeah, maybe like this. Yeah, so it brushes against the orange graph at only that point, that green point over there. Yes? Okay, and then this tangent line will have the same gradient as that point. Yeah, sounds like a good idea, but are you forgetting something? How many points do we need to find the gradient? We need 2 points, isn't it? We need 2 points. So we already have 1 point, right? By the way, we got this point because we were measuring. So let's suppose, let me explain a bit about how we got this point. So what we do is we have very good stopwatches and very good sensors. So as the apple is dropping, we record its position and we note down the time. So we probably have, say, a few of these coordinates marked down. And then we use a graph to smoothen out, yeah, to trace through all the points. Okay, so we have the points in blue and green. Okay, but to find the gradient, I will need another point where? On this green dotted line, right? Would I have any of these points? Ironically, I wouldn't, because again, the tangent line only touches the orange graph at one single point here, which means I will not have any other point on the tangent line itself. And then here comes the question, if you only have 1 point, how are you going to work out the gradient? You can't. Yeah? So this was a good idea, but we are missing 1 point. We are missing another point. Okay? And for those of you who are catching on very fast, you'll be like, hey, wait, look at this. We have so many points. We have 5 points on the graph. Why don't we just use 2 of the points on the graph itself, on the orange graph itself? Well, I'll say that's not a bad idea. But let's go to decimals. Let's go to decimals to show you what is actually going on here. Right? And I think I have to open this. Is this the one? Yeah, there you go. Okay, right. So over here, we have 2 points. Yeah, I need to hide the sidebar so you can see the other point here. Okay, so I have 1 point here, 0.185. So at 0.185 seconds, our green point over here, at 0.185 seconds, the apple is 0.0839 meters from the tree. And the second point over here says that at 0.78 seconds, the apple is 1.3225 meters away from the tree. Okay, and how do we find then, the gradient? Then we take y2 minus y1 divided by x2 over x1, which I would like to summarize is just rise over run, isn't it? It's just rise over run. Okay, so if I were to plot that out, I will be able to find the slope of this line. Yes, this will give me the slope of this black line. Whatever I just found, the rise over run, will be the slope of this black line. Then you ask yourself, hey, wait. I'm supposed to find the slope of what? I'm supposed to find the slope of the tangent line, remember? Okay, so I've also plotted out the tangent line on decimals. So you can see. Can you see that the tangent line, the red color dotted line, the slope is not the same as the black one, Huh? So even if you use 2 points on the orange graph itself, that is not a good approximation for the gradient of the green point, the tangent line at this green point, isn't it? So let's go back to the notes, right? And let's write this down. Hey, you know what? This is not a good approximation of the gradient that we want. I want the speed of the apple at this point. Yeah, so that's why I need the gradient at this point. But if I draw a straight line through, oops, sorry, that's a very bad straight line. I'm sorry, you would think that drawing straight lines is easy, but it's a bit tougher than I thought, right? But this is not a good approximation of the gradient at this point, right? No good at all. Then what do? Right? And this is where Newton and Leibniz discovered that, hey, if we do bring that point, the second point, closer and closer. What's another word for getting closer and closer? Starts with an A. If it approaches. Sounds familiar? Limits. Yeah? So as the x coordinate of the red point approaches the green point, what happens? The slope of the black line approaches that of the tangent line. Okay, in fact, we can say that it becomes the tangent to the point if we take limits. If we take limits, yes, it becomes the tangent to the point. Yeah? Cool, right? Yeah, so let's look at this. As it comes closer and closer, you can see the slope of the black line becoming exactly the slope of the red dotted line. Yeah? Okay, so next. Yeah, so you can see again Newton and Leibniz. Okay, of course, in reality, they didn't say this. They didn't get along, and they discovered this on their own, sort of. So Newton says, how small do you want to go? Right, and Leibniz replies, as close to zero as we can. So let's look at how to do this technically. Let's get down into the details. Okay, so Leibniz says we can make h even smaller. So what is h? Right, h is over here. Let me just very quickly draw this out so you can understand what we mean by making h smaller. Okay, say, oh, let me use blue. Right, let me use blue for this point. So this over here, imagine we do not know what this point is. Let this point just be something general like x. Then we let the second point, which is a distance away, right, to be x plus h. This is x plus h, which means that our x2 minus x1 is equals to h. Okay, now let's look at our y2 and y1. But before that, let me color this green. And let me color this red. Right, so it's similar to the example we've seen earlier. Okay, so let's suppose, again, this is a general curve. Right? I do not know what's the equation, but this is a function, f of x. Then what is the y value over here, or the point in green? It would be whatever the function is, you substitute the value, which is x, inside here. And then for this one, right, we just need to substitute x equals to, the input equals to x plus h. Yeah, so this will be y2, and this is your y1. Okay, so let's copy that down. y2 minus y1 will become this. Yeah, y2 minus y1 is f of x plus h minus f of x. Yes, which means if I wanted the gradient rise over run is very simply y2 minus y1 over x2 minus x1. This will be the gradient. This is also rise over run. All right. Okay, I'm going on to the next page so you can see this. Yeah. So both of them agree that, hey, we can find the gradient as long as we follow this. Right? Rise over run. But do you remember something? Yeah. The gradient is only accurate if we bring the two points closer and closer to each other, right? The green and the red point. Sorry, let me color it again. I need to bring the red point closer and closer to the green point. What happens when red gets closer to the green point? H becomes smaller and smaller. And we want it to be so small that it's almost zero. What do we need to do? We need to take limits. Right? So there you go. Okay? This is the limits. This is the first. This over here is the first principle of differentiation. Okay? This is the very basic, the most fundamental principle of differentiation, finding the gradient. It is essentially rise over run. Right? Nothing new from what we learned earlier. Rise over run. But we are taking the limits. And by taking the limits, we are making the 2 points for the gradient so very close to each other that is almost zero. Okay, so that is the first principle of differentiation. I will not check it off the checklist yet because I'm going to explain to you the beauty of this first principle. Okay, by first going through an example. And the example here is this. The example is, let's say our function is just x squared. Right, f of x is x squared. Okay, so that means f of x, okay, so you need to imagine, right, we have a machine that basically just squares whatever you put inside, right? Whatever input you put in, it gives you the square. So if I put in, say, a, then a square will come out. If I say put in b, then b squared will come out. But what if I put a plus b? Then you just square the whole thing, right? A plus b, whatever that is, you'll square the whole thing. Okay? So let's look at what happens if you put x into the machine. You get x squared, isn't it? If you put x plus h into the machine, what do you get? You get x plus h whole thing square. Okay, so that is our y2. This is y2. This is our y1. Okay, so if you look at the first step over here, see that this is y2 minus y1 over x2 minus x1. Okay, that doesn't change. It's still h. x2 minus x1 is still h. Okay, your x1 is over here. x2 is over here. Okay, x2 minus 1, x1 is h. Okay, next we're going to expand this one. Expanding this, we will get x squared plus 2xh plus h squared. Okay, and not to forget, we still have a minus x squared over here. So let's write that in, minus x squared. Okay, so before we move on to the next step, do you see in the numerator something we can simplify? There's a positive x squared here and a negative x squared here. If you combine the two of them, it becomes 0. It becomes 0. And then our next step, we just have this in our numerator. Okay? And then what I'm going to do is, remember, h is not 0. It is not 0. Because it's not 0, I can divide it. Okay? Remember that dividing by 0 is a big no-no in mathematics. You cannot divide by 0. So h is not 0. Therefore, we can divide it, top and bottom. Right? So it becomes 2x plus h. It becomes 2x plus h. There you go. And then here is where we take the limits, right? We say that, oh, you know what? As h approaches 0, it is just a very, very small number, 0.00001. And that is as good as saying, hey, this is just 2x log. But wait a minute. I'm supposed to find the gradient of the graph. Why is the gradient 2x? Well, this is why. Imagine if I wanted to find the gradient at this point. X equals to 0, right? What do you need to do? You substitute x equals to 0 inside here. And then what do you get out? Your gradient equals to 2 times 0. Your gradient is 0. Is the gradient 0 at this point? Right? All you need to do is draw a tangent line. Yeah, it's 0, right? It is 0 at the bottom, at the minimum point of our x squared graph. Okay, let's try another point. Let's try x equals to 1. Okay, let's substitute x equals to 1 inside here. What do we get for our gradient? We get the gradient equals to 2 times 1 equals to 2. So if you look at this point, right, over here, I'm just going to try and draw a line here. Yeah, the gradient looks like 2, isn't it? Gradient looks like 2. Let's just try one more point for fun. Huh? Let's try, say, x equals to 2. What happens? Then you get the gradient equals to 4, because 2 times 2 equals to 4. So somewhere over here, when x equals to 2, you'll find that the slope is very, very steep, about 4. And that makes sense because the x squared graph, right? As you go more and more towards the right-hand side, it becomes steeper and steeper, right? As x becomes bigger and bigger. So that makes sense. And yeah, this looks kind of like a function, isn't it? If you think about it. You substitute values in, you put values in, and you get outputs. And the output is a gradient. So this thing over here is what we call a gradient function. A gradient function. Okay? And we have a very special, can you see that it's not f of x? Right? F of x was our original function. Our gradient function is called f with apostrophe x. And we read this as f prime of x. So f prime of x is the gradient function for f of x. Yeah? Okay? So I am going to very sneakily, try and answer the 5th question on the checklist. Why sneakily? Is because if you think about this, 5 minutes ago, when I haven't shown you the gradient function, you would have agreed with question 5 on the checklist, because finding gradient does require 2 points on the graph. Yes? Yes. But what I've just shown you, the gradient function, if you just realize, I did not need 2 points. I only needed 1 point, right? So that our machine can take in the input and then churn out the gradient for you. Do you realize that? Very sneakily, I've shown you that, ironically, you can find the gradient with only one input. Okay, with the gradient function, with differentiation. Okay, so this is the beauty of differentiation. You are no longer bounded by the natural law of like, hey, you know what? If you want to find the speed of a car, you need to give me 2 points in time. Not anymore. If you have algebraically the distance time graph or the distance time function of your car, I only need 1 point to tell you the speed of the car. Isn't that amazing? Yeah. So I'm going to check off question number 5 because it is an oxymoron, right? I first tried to convince you it's 2 points, but now I've shown you that, hey, you can do it at 1 point. And that I feel is the beauty of, okay, let me go back one page. And that I feel is the beauty of the first principle of differentiation. That is so beautiful, right? It is so sneaky, right? Like we are using 2 points, but they're so close together, we consider it as 1 point. And it is so convenient for us, right? As you'll see later on when we apply this to real life situations. Okay, and that wraps up this lesson, right? For this video. Thank you for watching. I hope you enjoyed it. I hope your mind is blown by how beautiful differentiation is. I certainly enjoyed making this video. And yeah, if you like it, stay tuned for the next one. We have even more fun things to look at for differentiation. We've only just started. So till then, catch you on the flip flop.